Today I'll introduce one of my favorite problems I've come up with. I haven't researched too much, so it's possible it may be a duplicate, but nevertheless, the problem statement goes as follows. We're given a tree to you with less than 10 to the 5th nodes. In place on the tree are n rabbits such that every rabbit is on exactly one node. Rabbits come in pairs. That is, every rabbit has a partner rabbit. Moreover, a rabbit's partner's partner is itself. Our task is to output the minimum amount of swaps of rabbits in order to get every rabbit adjacent to its partner, or -1 if no such sequence exists. We'll go over an example shortly, but I do want to place particular emphasis on the fact that this might not even be possible. Here's an example tree to highlight the problem. Nodes with the same color indicate partner rabbits, and note that the initial arrangement is given to us. You can try playing around, but we can show that the minimum amount of swaps required to make adjacent nodes have the same color is 3. In fact, we can even see a possible sequence here. As we can see, at the end of the sequence, all rabbits are with their partner. Let's return to solving the main problem. To do so, we'll focus on the case of whether or not the task is even possible. This is useful because this is a decision problem rather than an optimization one. Moreover, it's still related to the original problem, and therefore we hope that the insights we gain during this process can help us solve the more general version. There's a few reasons we might suspect that a given instance has no solutions. For one, if n is odd, then there's trivially no solution, but that's pretty boring. One possible reason of substance is that maybe the initial arrangement somehow leads to a trap, and therefore we must output -1 on this particular starting condition. Phrased more precisely, it might be the case that one arrangement of the tree U has no solutions, whereas another arrangement of the tree V has solutions. However, we can quickly see this will not be the case. In particular, since V is solvable, then there must exist a sequence of moves that leads from V to a final state where partner rabbits are adjacent. That's the definition of V being solvable. Then it's intuitive that we can compose a sequence of moves that takes us from U to V, and if this is a bit hard to see, notice that we can greedily match nodes one by one until we match the entire tree. From here, we can compose the two sequences and find that there is in fact a path to go from U to an accepting state. Is this the most optimal route? Likely not, but remember that for now we are just focusing on whether or not a problem has a solution. Alright, but that assumed that one configuration had a solution. Maybe there are some trees where all configurations have no solution. In fact, this can be true even when n is even. Let's look at this example. No matter how you arrange the rabbits, there will be at least one partner that is separated. And in fact, since we're only looking at the tree structure, we can color all nodes black and focus on the raw tree. Note that for a solution to exist, it is sufficient to find a partition of the tree into adjacent nodes. That is, we know that at the end of the summation there's going to be a rabbit at any given node, and that rabbit must be adjacent to its sister. Therefore, we have to see if we can partner off all nodes with one of their neighbors. In these types of problems, it's helpful to think about the root and leaves, which if you're unfamiliar are somewhat the topmost and bottommost nodes respectively. It might not be clear how we can partner off the root, but with the leaf there's only one choice we can make. We are forced into partnering it with its parent since it has no other neighbors. We can do this for every leaf. Now, once we partner all of these guys off, it might seem that we're stuck. However, the key realization is that there's again a bottommost layer where every node's only active neighbor is its parent, and thus its partner is forced as well. It's almost as if they're a new set of leaves. Therefore, we can continue on with this process, and just like that, the entire partition is forced. Now, if we go back to the bad tree, we can see why it's impossible to get this to work. Once you partner one leaf, the other leaves had their partner stolen from them. We'll denote these pairs of nodes as metanodes, and the algorithm that solves it as metanode partitioning. If you're curious, this can be implemented using topological sort. Regardless, this brings us the following idea. A tree is solvable if and only if the metanode partitioning doesn't reach an inconsistency, such as what we saw in this bad tree. Moreover, if a partition exists, it's unique. We know this since our partition was completely forced upon us. We had no choices at all when making it. Let's return to the main problem. But before I do, I want to emphasize the notion that graphs are really about relations. It's almost always helpful to focus on the edges in a graph as some relation between nodes, even if that's somewhat abstract. Here's an example arrangement, and I'm going to draw the metanodes over this tree. While this might be somewhat hard to motivate, there's actually a completely separate graph in this picture. In particular, the nodes of this new graph are going to be the metanodes. From here, I think we can agree that, in some abstract sense, two metanodes U and V are related when U contains the sister of a rabbit that V contains. Therefore, this relationship is going to provide the edges for our graph. Let's actually see how this graph looks like. Well, a physical drawing might not be that helpful, so let me present another way to visualize this. We can start with an arbitrary metanode. Then, notice that it will have two edges since it contains two sister rapids. Let's traverse one of the associated edges, visiting the metanode that contains the sister. From here, the new metanode we visit again has two edges, but we already traversed one, so let's go along the other. We can do so again on the third metanode, but then we return back to the start, forming a cycle. If we instead started from one of the other metanodes, we would have gotten a two-cycle instead. Another thing to point out is how this auxiliary graph looks like when the tree is solved. In fact, since every metanode must contain the two sisters, the only edges will be self-loops. Somehow, this seems like a tangible goal. That in our case, the initial auxiliary graph was a set of cycles, but can we be sure this is always the case? In fact, we can. Once again, note that all nodes have degree 2 by virtue of the fact that they contain two rapids. We have to be a little careful on self-loops and two cycles, but it does work out in the end. My claim is that this first fact implies the second. To see this, let's generalize the process we did at the beginning. Let M be a sequence of metanodes with M0 being chosen arbitrarily. Then let M1 be the node we get when traversing any of M0's two edges. From here, we can visit M2 by traversing the edge from M1 that hasn't been traversed, which we know must exist since all nodes have degree 2. Likewise, we can visit M3 and so on. We can continue with this process indefinitely and get an infinitely long sequence. The sequence is infinite, but any particular position can only take on finite values as the number of metanodes is finite. By the pigeonhole principle, this means that we must have a repeat somewhere. Let I be the index of the first such value, and j be the associated repeated index. A priori, it might be the case that I equals 3 and j equals 7, for example. However, this cannot be true since then mi would have a degree of 3, which is a contradiction. The only possible value of I is 0. If you think about it, this implies that we in fact have a cycle. We can repeat this M sequence for any metanode in the graph, and therefore partition the graph into a set of cycles. With this in mind, the last step is understanding how the auxiliary graph changes. Remember that our goal is to transform this graph into one where every metanode is in a self-loop. Phrased differently, we want to split each cycle such that we're left with n over 2 connected components, since there's n over 2 metanodes. Now let's look at how a swap affects the graph. There's a few possible cases to consider. When we perform a swap, most of the graph is actually unchanged, but the metanodes related to the swapped rabbits might have to be slightly modified. In some situations, the swap results in a flip of the cycle, but nothing principally changes in terms of the number of components. Some swaps are bad and merge two cycles, decreasing the number of connected components by 1. Other swaps split a cycle into 2, increasing the number of components by 1. And as a sanity check, everything is reversible. In fact, these are all the possible situations. This actually gives a lower bound on our answer. We start off with C connected components, but a single swap can increase the number of components by at most 1. Therefore, we will need at least n over 2 minus C swaps to solve the graph, with the n over 2 coming from the final number of connected components we need to achieve. We can actually achieve this lower bound by simply greedily removing a single sister rabbit pair from the cycle in any given move. Since we constructed a solution that matches the lower bound, we have our answer. Next, let's take a look at how this works in practice. Here's the same algorithm of greedily reducing cycles applied onto the original tree. Here's a quick recap. First, we determined when the solution even exists. This led us to the discovery of metanodes and the fact that the partition of the tree is unique. We then realized that among the metanodes, there is a natural relation that gives rise to a permutation graph. This permutation graph allows us to establish a lower bound, to which we then provided a constructive solution meeting that lower bound by greedily matching sisters. This verifies the correctness and optimality of our solution. This video was made using monochrome. I have a behind the scenes video on how it was made.